Okay, let's dive in. Think about every digital signal, all that data flying around or stored somewhere,
Hmm.
phone calls, streaming, even signals from deep space probes, they all face noise interference.
It's the constant battle, yeah.
And that's where error correction codes step in. They're kind of the unsunny heroes, making sure your data actually arrives correctly even when things get messy.
Absolutely. They add redundancy, these little checks and balances, so you can spot errors and sometimes even fix them automatically. But the heavy lifting, that's the decoding.
Right, figuring out the original message from the noisy version you received.
Exactly. And traditional ways of doing that, the algorithms, they can be complex and sometimes just not fast enough or accurate enough for what we need today.
Which is where AI has really started to, shake things up. We've seen this huge wave of using neural networks for decoding.
Yeah, it kicked off around, 2016? People started by taking classic algorithms like belief propagation and sort of embedding them in neural nets, neural belief propagation, things like that.
Teaching the networks the rules, basically.
Right, learning the update steps. But then came the other approach model, free.
More data-driven.
Exactly. Just treat it like a mapping problem. You feed in the noisy signal and you train the network. Could be anything from simple networks to diffusion models or, importantly, transformers.
Like the ECCT, the error correction code transformer.
Precisely. And these neural decoders, they've shown real promise, often matching or even beating classical methods on certain types of codes.
But there's a catch, right? Our sources point this out.
There's always a trade-off, yeah. The ones that perform the best tend to be computationally expensive.
Not great for real-time stuff.
Nope. And the faster ones, they might lag a bit in performance, accuracy-wise.
Which sets the stage perfectly for the research we're unpacking today. A new decoder designed to, well, get the best of both worlds.
The ECCM, Hybrid Mamba-Transformer Decoder.
Hybrid. It combines two pretty cutting-edge AI architectures, Mamba and Transformer.
And we've got some great source material for this deep dive notes on the research timeline, who the key players are, a study guide, and crucially, parts of the actual research paper.
Yeah, detailing the architecture, the experiments, the whole 9 yards.
So our mission today isn't just to describe ECCM. We want to get into the why.
Why these specific choices? Unpack the core innovations, the clever technical bits.
Especially how they bake in that code knowledge. And then look at the results. What do they really tell us?
Okay, let's set the scene first. Error correction codes. You encode data. These codes have rules, right? Defined by a parity check matrix, H.
That's the rule book. If X is your original error-free data block, then HX equals 0. That's the fundamental check.
And the typical scenario they model is sending data over a noisy channel, like additive white Gaussian noise, AWGN, using BPSK modulation.
Common setup. So the receiver gets Y, which is X plus noise. And the decoding problem is, given this noisy Y on the rulebook H, find the most likely original X.
And we mentioned the history classical algorithms like belief propagation, min-sum.
Then the neural approaches, model-based, learning the steps.
And model-free, learning the direct noise to correction mapping, like ECCT.
And the big challenge ECCM is tackling, that performance versus speed problem. How do you get accuracy and speed?
So ECCM, the Mamba-Transformer hybrid, why this specific combination? What's the thinking?
Okay, that's really the core idea. Transformers, as we know, are fantastic at seeing the big picture, global context.
Their attention mechanism can link any 2 points in the data, right?
Exactly, which is vital for understanding long-range dependencies in codes, especially complex ones like LDPC codes.
But like you said, that global view is computationally expensive, doesn't scale well with longer blocks.
Precisely, and that's where Mamba shines. Mamba is built for efficient sequential processing. It uses a state space model core with a smart selection mechanism.
So it scales better, lower latency?
Much better for long sequences, yeah. Lower runtime latency during inference. It's good at processing information along the sequence efficiently.
So the hybrid idea is global view from Transformer, efficient sequential processing from Mamba.
You got it. Get the strengths of both. They structured ECCM with alternating layers. Starts with Mamba, then Transformer, Mamba, Transformer, and so on for layers.
So Mamba handles maybe local stuff and initial processing quickly.
Right, leveraging its speed and scaling. And then the Transformer layers come in periodically to integrate that global context. Look at the long-range interactions. It's like having two specialized tools tag-teaming the problem.
Clever. And the input they use, it's not just the raw noisy signal Y, is it? They use the amplitude Y and the syndrome S.
Good point. That's another smart detail, building on earlier work. The syndrome, S, tells you which parity checks are failing. It flags where errors might be.
And the amplitude?
The amplitude, Y, tells you how reliable each received bit is, how confident the receiver is about whether it was a +1 or a -1.
So combining reliability and the error flags.
Right. It makes the input invariant to the actual transmitted code word, +1 or -1. It forces the network to focus directly on the error pattern and the confidence levels, not the original message itself. Helps prevent overfitting, makes it learn better.
Okay, hybrid architecture, smart input, but the really novel stuff, the main academic contribution, seems to be how they integrate knowledge of the code structure, that parity check matrix H, into the network.
Yes, this is where it gets really technical and, frankly, pretty cool. They aren't just stacking blocks. They are embedding the code structure deep inside the network's calculations. At every layer, using masking.
Masking, like blocking certain connections.
Kind of, yeah. The goal is to force the network's internal computations, whether it's the attention in the transformer or the state updates in Mamba, to only consider bits that are actually related by the code's parity checks. Remember HX equals 0? That defines the relationships.
So they're baking the code's graph structure right into the neural net.
Exactly. And they need different masks because Mamba and transformer work differently inside.
Okay, so what's the mask for the transformer layers?
They use a mask called GH. This isn't entirely new. It builds on work like ECCT. It's applied during the attention calculation.
How?
It effectively zeroes out or sets to negative infinity the attention scores between any pair of bits that don't share a common parity check, according to H.
Ah, so the transformers is forced to only pay attention to bits involved in the same check.
Precisely. It drastically cuts down the computation for attention and forces it to focus on the code structure. Figure 1D in the paper shows this visually.
Okay, GH for transformer, focuses attention. What about Mamba? This is where their new mask comes in, right?
This is the big one, yes. A novel contribution. They created a mask specifically for Mamba called FH.
And what does FH look like?
It's structured as HI, so it combines the parity check matrix H with an identity matrix. They apply this mask F of H inside the Mamba layer, specifically to the internal matrices of the selective state space model, the SSM block. You can see where in figure 1B.
Okay, applying that mask to the Mamba internals, what does it achieve?
It does something analogous to the transformer mask, but for Mamba's sequential state updates. It ensures that when an input bit influences the Mamba state, that influence is restricted only to other bits or state components connected via a parity check line in H.
So it's guiding Mamba's state updates along the lines defined by the code structure.
Exactly. They found a way to impose the code structure onto Mamba's state dynamics. It's not just processing sequentially anymore. It's processing sequentially along the graph defined by H. Really clever engineering.
That's a huge difference. Okay, so code-aware masking, tailored for both architectures. That's innovation one. What's the second big piece?
The progressive layer-wise loss. This is about how they train the network.
Instead of just one loss at the very end.
Right. Normally you calculate the error only on the final output and backpropagate. Here they calculate a decoding loss, specifically binary cross entropy, between the layer's output estimate and the true error vector at the output of every single layer. Mamba layer, transformer layer, each one gets a loss calculated.
And they sum all these losses up.
Yep. The total training loss is the sum of the losses from all intermediate layers plus the final layer.
Why do that? Seems like more work during training.
It is more computation during training, but the payoff is substantial, especially for these deep networks. First, it provides much stronger gradient signals deeper in the network, helps train those early layers better, fights fantasy gradients.
Okay, better training dynamics.
But more than that, it encourages every layer to learn a useful decoding step. Each layer is pushed to improve the estimate of the error pattern. The ablation study they did shows this was a massive factor in their performance gains.
And it enables something else too, right? Early stopping.
Exactly. Because each layer produces an output estimate, you can check the syndrome after each layer during inference. If an intermediate layer, say layer I, produces an output whose calculated syndrome psi matches the input syndrome S.
You know you found a valid code word?
Potentially the correct one, yes, so you can just stop decoding right there. Figure 1C illustrates this. At higher signal-to-noise ratios, where errors are fewer, this can save a lot of computation time.
That layer-wise loss is smart. Intermediate supervision driving performance and enabling speedups. Okay, so innovations, hybrid structure, the two code-aware masks, especially the novel FFH for Mamba, and this progressive loss. How did it actually do in tests?
They tested it thoroughly. Used standard codes, BCH, Polar, LDPC, McKay codes from a public database. Simulated the AWGN channel across different noise levels, SNRs. Measured performance using the negative log of the bit error rate, Nellis NBER. Higher is better.
And the results. Table 1, Figure 2.
Pretty impressive. For BCH and Polar codes, ECCM consistently outperformed the previous best neural decoders, like ECCT and AECCT. They cite improvements up to 18% in LNBER.
Significant gains there. What about LDPC codes?
More mixed, but still strong. It was competitive with, sometimes slightly better than ECCT, although another model, Cross-MPT, did better on some specific LDPC codes. Shows different architectures might have different sweet spots.
Interesting. And the McKay code?
ECCM clearly outperformed all other tested models on that one, which is notable because McKay codes have sparse structures, suggesting ECCM is good at learning those sparse dependencies.
So strong performance, especially on BCH, Polar, and McKay. But speed was the other big goal. How did it compare on inference time?
That's where the Mamba part and the masking really shined. Tables 3 and 4 show ECCM is substantially faster than the other neural decoders they compare against.
Like how much faster?
For one example, the LDPC 4924 code, it was almost 3 times faster than the next best neural method at inference. That's a direct result of Mamba's efficiency and how the masks reduce the computational load in both Mamba and transformer layers.
And the early stopping kicks in at higher SNRs to make it even faster.
Exactly. Table 4 shows that effect. As the signal gets cleaner, it finds the answer earlier in the network layers, stops, and saves time.
Okay, performance and speed look good. Did they dig into why it works so well? The ablation studies and attention analysis.
Yes, those are key to understanding the contribution of each part. The ablation study, Table 2, is where they systematically remove one piece at a time and retest.
And the takeaway. What mattered most?
The progressive layer-wise loss. Taking that out caused the biggest drop in performance. It really confirms how crucial that intermediate supervision is for training this kind of deep hybrid model.
What else did the ablations show?
It confirmed their novel F-H Mamba mask was better than just trying to use the Transformer's GH mask in the Mamba layers. And importantly, the full hybrid structure beat a Transformer-only version. The combination itself provides real value.
And the attention analysis. Figure 5, Table 5, what did looking inside the Transformer layers reveal?
They visualized the attention scores. One clear finding was strong attention involving the syndrome input, showing it acts as a kind of reference point, which makes sense.
But the really interesting bit was related to errors, right?
Yes. When a specific bit position actually has an error, they saw a noticeable increase in attention across the entire column corresponding to that bit in the parity check matrix H.
Meaning
the network learns to look at all the parity checks that involve that potentially faulty bit. It's using the code's defined structure, guided by the mask, to investigate the error by checking all related constraints.
That's fascinating. It suggests the network isn't just pattern matching, it's actively leveraging the code analytical structure.
Precisely. The masking does more than just speed things up. It guides the network to learn these structurally meaningful relationships. It seems to do this more effectively than some prior models reportedly did.
So, looking forward, what are the limitations here? Where does the research go next?
Well, the authors themselves note a couple of things. Most tests were on moderate block lengths. How well it scales and generalizes to very long codes, or non-binary codes, codes using alphabets larger than just 0 and 1 that needs more study.
And complexity.
While it's much faster than previous neural decoders, it's still a complex neural network. Compared to the very simplest classical decoders, it might still be too heavy for extremely resource-limited devices, like tiny sensors.
But the potential impact seems massive.
Oh, absolutely. Making error correction faster and more accurate is fundamental. Think 6G wireless, satellite communications, deep space missions with weak signals, even just reliable data storage. Improvements here ripple outwards.
Although, there's still that black box issue with learned decoders, isn't there?
That's the elephant in the room for the whole field, really. For safety-critical systems, think medical devices, autonomous vehicle controls, you often need guarantees. Certifiability. Classical algorithms, you can often mathematically prove their properties.
Harder with complex neural nets.
Much harder. Even with great performance, understanding exactly how they'll behave in every single possible situation, proving they won't fail unexpectedly, is a major challenge. Interpretability and formal verification are lagging behind performance gains.
Okay, so let's wrap up this deep dive. ECCM, it looks like a really significant step forward in learned error correction.
Definitely. It's a state-of-the-art decoder that cleverly mixes Mamba and Transformer. And those key innovations, the hybrid design, the tailored code-aware masking, especially that new FH mask, and the progressive loss they really deliver.
Better accuracy on important codes, substantially faster inference than prior neural methods.
It's a great case study in how you can merge modern AI architectures with deep domain knowledge like coding theory to create something powerful.
Pushing the boundaries of performance and efficiency for a really fundamental digital technology.
Exactly. It changes how we might think about designing decoders in the future.
So here's something to chew on as you go about your day, using all this technology shielded by error correction codes you never see. We have these incredibly powerful learned models like ECCM achieving amazing performance gains, but they are complex, maybe harder to fully trust or verify than older methods. So how do we square that circle? How do we best use the power of these AI models for critical infrastructure like communications and data storage, while still ensuring the absolute reliability and trustworthiness we need? What does the success of an approach like ECCM, which explicitly blends AI with coding theory structure, tell us about the future synergy between fundamental theory and advanced machine learning?